Hello Sleepy Science subscribers, welcome to the channel. Please do not forget to like and subscribe so more people can benefit from these calming journeys. Tonight, we begin a gentle and slow exploration of a question that has fascinated philosophers, scientists, and dreamers for centuries. Could reality itself be a simulation? As you settle into a comfortable position, allow your breathing to slow and soften while we drift together into this calming universe of ideas. Our goal tonight is not to prove or disprove anything, but to create a peaceful space in your mind where curiosity flows like a quiet river and every thought moves with soft intention. Imagine for a moment that everything around you is woven from threads of information, each thread glowing faintly like dust illuminated by moonlight. Some scientists suggest that the universe may not be built from matter at the deepest level, but from patterns of data. This idea does not need to feel frightening. It can instead feel soothing, a reminder that reality might have structure, order, and quiet design. When we picture the universe as information, we begin to see it as something stable and gentle, something that moves with purpose. The philosopher Plato once described a cave where people could see only shadows on a wall, believing those shadows were the entire truth. Although this idea came long before computers, it carries a similar message. What we see might be only a small layer placed gently over a deeper reality. The world might be more complex, more structured, and more mysterious than our senses can detect. Thinking about this can create a sense of soft wonder, not tension, not worry, just wonder. The type of wonder that helps the mind drift toward rest. In modern times, thinkers like Nick Bostrom expanded the question even further. He proposed that if any advanced civilization ever gained the ability to simulate entire universes, then there would be countless simulated worlds and only one original world. If that is true, then mathematically speaking, it might be more likely that we are inside a simulation rather than outside it. This idea may sound strange at first, but when approached gently, it becomes almost comforting. It suggests that our universe may have rules because it was made with intention, that our reality follows patterns because those patterns were designed with care. Breathe slowly and imagine the universe around you as a vast grid stretching in every direction, each point glowing softly with potential. The laws of physics act like the rules of a grand cosmic program, always consistent, always stable. They do not shift suddenly or break without reason. They move like tides, slow, steady, predictable. This predictability is part of what makes life feel safe. The universe rarely surprises us with chaotic changes to gravity or lighter time. Everything flows in a familiar rhythm. Some physicists believe that space itself might be made of tiny, indivisible units, like pixels on a screen. If this is true, then the smoothness we see in the world is simply the result of extremely small building blocks, not imperfections, not glitches, just structure. Imagine drifting above a quiet cosmic ocean filled with stars that shimmer like particles in a softly rendered simulation. Whether simulated or natural, the sight remains beautiful, calm, harmonious. Quantum mechanics adds more quiet mystery. Particles sometimes behave like waves of probability until they are observed. Some thinkers wonder whether observation acts like a rendering process, similar to how a computer fills in details only when needed. This does not prove anything, but it is a peaceful image. A universe that reveals itself gently. A universe that waits patiently for attention before taking shape. Like morning light slowly revealing the outlines of a room. Whether reality is a simulation or not, the question itself can create calm reflection. It reminds us that the universe is full of mystery, full of subtle patterns, full of gentle possibilities. Tonight, let your thoughts drift without pressure, without urgency. Whether real or simulated, the universe around you remains steady and serene. Its quiet beauty carries you toward a deeper state of rest, towards softness, towards sleep. As we continue this quiet exploration, allow your breath to move gently in, out, while your mind drifts deeper into the soft landscape of possibility. The idea that our reality could be a simulation is not meant to disturb your sense of self or safety. Instead, it offers a slow and steady way to think about the universe. Like watching distant stars from a calm hilltop at night, everything remains peaceful. Everything remains steady. You are simply opening a window to a new perspective. A window that lets the imagination stretch out like a quiet horizon. Think for a moment about the consistency of the universe. Every day, gravity behaves the same way. Light travels in a straight line at a constant speed. Atoms follow the same rules everywhere. These patterns repeat across the cosmos with an almost perfect rhythm. It is this rhythm that some scientists compare to the rules of a vast program. Not because they believe the universe is artificial, but because the structure resembles a coded system. Something stable, something uniform, something that does not drift away from its own laws, like a melody that never loses its tone. If reality were simulated, some researchers say it might run on what could be called computational efficiency. In a computer program, details are rendered only when needed. In a simulation, unnecessary complexity is avoided to maintain stability. Some thinkers wonder if the universe behaves the same way. For example, distant regions of space appear completely uniform, as though they were created by the same simple rules rather than individually crafted. This does not prove anything, but it fits gently into the idea. A universe optimized for elegance. A universe created through simple foundations that unfold into great complexity. Now imagine an empty field stretching farther than the eye can see. The grass bending under a slow and steady breeze. Above you, the sky glows with pale light as faint clouds drift like soft fabric. You can picture this scene clearly in your mind because your brain fills in the details automatically. It renders the field, the sky, the texture of the ground beneath your feet. In a similar way, some scientists say the universe may reveal details only when needed, when observed, when interacted with. This idea has echoes in quantum mechanics, a field of probability collapsing into a defined state only when something calls for it. There is a peaceful quality in imagining the universe working this way, slowly, efficiently, quietly. Rather than chaos, everything moves with purpose. Stars form because the rules allow it. Galaxies spin because the laws create balance. Atoms bind together because the foundation of the universe guides them into harmony. Whether these rules come from nature or from a constructed framework, the result is the same. A cosmos filled with order. A cosmos where patterns repeat with gentle reliability. A cosmos that cradles the mind as it seeks rest. Some thinkers also explore the idea of digital physics, the suggestion that the universe may behave like a giant information processing system. Space could be a grid of tiny units. Time could move in discrete steps. Energy and matter could be storage and transfer of information. If this is true, then the universe might resemble a simulation, not metaphorically, but literally. Every event could be a calculation. Every particle could be a data point. And yet this concept does not reduce the beauty of existence. It only shifts the perspective. Instead of being a random place, the universe becomes a structured and meaningful environment. Let your thoughts float gently around this idea. There is no pressure to decide whether it is true or false. Most scientists do not claim certainty about the simulation hypothesis. They simply explore it with curiosity. One physicist might say that the mathematical nature of the universe hints at deeper structure. Another might say that the theory is interesting but unprovable. These varied perspectives blend into a calm landscape of possibilities. You are not required to choose a side. You are only invited to observe the ideas passing quietly, like clouds in a slow-moving sky. Imagine drifting deeper into the universe now. Picture the Milky Way as a quiet river of stars stretching across the cosmic darkness. Each star shimmering softly like a pixel in an immense image. The glow of distant galaxies forms gentle patterns, as though the universe itself is arranging information into beautiful geometry. Whether these shapes arise from natural laws or from programmed rules, the effect is the same. A sense of order, a sense of balance, a sense of peaceful continuity. The mind naturally wonders about purpose when considering these ideas. If the universe were simulated, what would be the reason? A scientific experiment, a creative project, a historical reconstruction, or perhaps something beyond human understanding. While these questions can feel heavy, they do not have to be. You can let them drift, softly, without urgency, like watching ripples fade across a quiet lake. The purpose is not to reach an answer, but to relax into the mystery, to let curiosity expand without fear, to allow the gentle unknown to become part of your journey into rest. Whether reality is natural or simulated, the experience of living remains the same. The feel of warmth, the sound of a quiet room, the softness of breathing. These sensations are real to you. They ground you in the present moment. They offer stability, comfort, peace. Let this awareness sink gently into your mind as you continue to drift. The universe, whatever its origin, remains steady around you, holding you, supporting you, guiding you gently towards sleep. As we continue drifting deeper into this calm exploration, allow your body to sink a little more into comfort. Let your shoulders loosen. Let your breathing soften. Each slow inhale and gentle exhale brings your mind into a quieter state where thoughts stretch out like long, peaceful waves. The idea that our reality might be a simulation may sound complex, but when approached slowly, it becomes a pathway into contemplation rather than confusion. A doorway that opens not into worry, but into wonder. Tonight, we simply allow this possibility to unfold like a soft horizon. Think for a moment about numbers. Not the sharp, busy numbers you see in daily life, but the quiet ones that guide the structure of the universe. The ratio of a circle, the behavior of waves, the patterns of orbits. These numbers appear everywhere. In galaxies, in atoms, in the movement of rivers, in the spirals of shells. Many scientists find it fascinating that the same mathematical rules apply from the smallest particles to the largest clusters of stars. This universal consistency creates a sense of design, not necessarily an artificial one, just a structured one, gentle, predictable, calm, nutty. Some researchers say that if a civilization advanced enough to simulate a universe existed, it would likely design it using simple, elegant rules. Because simple rules create stable systems, and stable systems allow complexity to rise slowly over time. Our universe seems to follow this principle. A few natural laws, a few constants, a few quiet rules that guide everything from the spin of electrons to the expansion of galaxies. When viewed from this angle, the universe resembles a beautifully efficient program. Smooth, balanced, purposeful. Imagine now that you are floating through a silent cosmic corridor. The stars lining the edges like lanterns suspended in endless darkness. Their light falls gently across the emptiness. Not harsh, not bright, just soft enough to guide your path. In this corridor, the laws of the universe feel almost tactile, as though you could reach out and sense the gentle mathematical fabric that holds everything in place. You drift in this silence, feeling the universe breathe slowly around you. A breath made of energy, pattern, dot, structure. Quantum physics adds another layer to this quiet idea. Some particles behave as if they exist in multiple states until observed. Some appear from empty space for a brief moment before vanishing again. This shimmering unpredictability seems chaotic at first, yet beneath it lies another pattern, a probabilistic order, a gentle wave of possibilities that collapse into form only when interaction occurs. Some thinkers compare this to how a simulation might reveal details only when needed to save resources. But whether or not that idea is true, the image it creates is calm. A universe unfolding slowly only when watched. Take a deep, slow breath now. Let your mind drift to the idea of resolution. Just as a digital image has pixels, reality may have a smallest unit of space, a limit beneath which nothing can be divided. If this is true, then the universe might have a grid-like foundation, like an invisible net that holds everything together. You cannot see these units. You cannot touch them, but their existence would mean that space is not infinitely smooth, but gently segmented. This segmentation would not feel artificial. It would feel natural, like the grain of wood or the weave of fabric. As you drift through these thoughts, you may wonder why people even ask whether reality could be a simulation. Part of it comes from curiosity. Part of it comes from the search for meaning. And part of it comes from the surprising alignment between digital systems and physical laws. Computers use binary code to represent information. The universe might use something similar. Not ones and zeros, but patterns, frequencies, fields. These patterns could be the foundation of everything we see and touch. If so, then physical objects would simply be arrangements of information. Stable, consistent, real to our senses. Some scientists like to think of the universe as a giant information processor. Every event is a transformation of data. Every interaction is an exchange of information. Energy becomes matter. Matter becomes energy. Particles communicate through fields. All of these processes resemble instructions in a vast cosmic algorithm. Slow, steady, predictable, elegant. When viewed this way, the universe becomes less like a chaotic system and more like a calm, flowing structure. A structure that gives shape to stars, planets, and life itself. Let your thoughts soften as you picture this. A universe built not from cold machinery, but from luminous information. Each particle shimmering like a tiny point of light in an endless digital ocean. Each law of nature guiding the flow of this light like gentle currents. You drift through this ocean weightless and calm. Every wave of information moves with purpose. Every ripple carries meaning. Whether this ocean is natural or simulated does not change its beauty. It remains a place of harmony and quiet wonder. Even if the simulation idea is never proven, the act of imagining it can be comforting. It reminds you that reality might be deeper than what appears on the surface. It reminds you that everything has structure. Everything has balance. Everything has rhythm. These rhythms guide your own life. The rise and fall of thoughts. The flow of emotions. The steady movement of breath. When you align yourself with these rhythms, you feel grounded and calm. The universe supports you whether it is simulated or not. Let your mind drift now. Softly, slowly. The question of whether reality is a simulation becomes less important than the peace found in thinking about it. There is no urgency, no pressure, only the gentle awareness that the universe around you is stable and serene, that every moment carries you closer to rest, that every thought settles like dust, gently falling onto a quiet surface. Allow this softness to fill your mind as you drift deeper into this journey. As we drift further into this gentle exploration, let your body rest a little deeper into stillness. Feel the calm weight of your limbs. Feel the slow rhythm of your breathing as it moves in and out like a quiet tide. Each breath softens the boundary between your thoughts and the peaceful darkness around you. This state of calm is the perfect place to continue reflecting on the possibility that our reality might be a simulation, not as a rigid theory, but as a soft idea, an idea that invites curiosity rather than tension, an idea that lets the mind stretch comfortably into wide open space. Consider how the universe behaves with such remarkable precision. Stars form according to exact patterns of temperature and pressure. Planets follow predictable orbits that remain stable for billions of years. Even the behavior of atoms repeats with perfect consistency. This extraordinary order leads some thinkers to wonder whether the universe might be following underlying instructions. These instructions would not feel mechanical. They would feel like the natural rules of a beautifully crafted world. A world with balance, a world with harmony, a world that invites life to grow quietly within it. Picture yourself floating through the vast darkness of interstellar space. The stars glow like tiny, soft lanterns scattered across an infinite canvas. Their light flickers gently through the void, carrying a sense of age and memory. The space between them feels peaceful and endless. As you drift through this darkness, imagine that every star, every planet, every part of a greater pattern that flows from a deeper layer of reality. Whether that layer is natural or simulated does not change the beauty of the cosmic scene unfolding in your mind. Think now about complexity. In nature, complexity often rises from simple rules repeated over time. Snowflakes form intricate patterns from basic chemical principles. Crystals grow from repeated atomic structures. Even the branching of trees and the shape of rivers follow simple mathematical rules that create breathtaking designs. If the universe were simulated, a similar idea might apply. The rules would be simple. The results would be vast. The beauty would emerge slowly and naturally, not forced, not artificial, just gently unfolding. Some scientists explore what they call emergent behavior. This is when simple systems create complex results without any central control. In a simulation, simple rules could generate galaxies and life in the same way simple equations create fractals. Fractals are shapes that repeat at every scale. They appear in clouds, coastlines, mountains, and even in the patterns of our own bodies. The universe seems to be filled with such repeating beauty. These repeating patterns create a sense of intentional design, a sense of quiet order beneath the visible world. Now think about the flow of time. Time moves forward in a steady rhythm, never backward, never sideways, always forward. Some researchers suggest that time could be like the ticking of a cosmic clock. Each moment, a frame. Each frame, a tiny step forward. If the universe were simulated, the flow of time might mirror the way a program updates in gradual cycles. But even if this idea is only metaphorical, the image remains calming. A universe unfolding frame by frame. Slowly, gently, predictably. Take a slow, deep breath. Imagine that each breath brings you closer to the quiet core of the universe. A place where information and energy flow together. A place where the laws of reality hum softly like a distant melody. In this quiet place, the simulation idea becomes softer, less like a theory, more like a dream that suggests the universe may have deeper layers waiting quietly in the background, layers that guide the movement of galaxies and the formation of thoughts, layers that create stability in a world that sometimes feels chaotic on the surface. Even the human brain processes reality in ways that resemble simulations. It predicts the world based on limited information. It fills in missing details. It smooths out noise and generates its own internal images. Some scientists say that your perception of reality is already a simulation created by your own mind. Not artificial, not digital, just a natural interpretation of sensory information. When viewed this way, the idea of a simulated universe does not feel foreign. It feels like an extension of the way consciousness already operates. Let your mind wander through this idea. Slowly, softly. Imagine that reality might be a layered system. At the top is the world you see and touch. Beneath that are the laws of physics. Beneath that might be patterns of information. And perhaps beneath those patterns could be something even more fundamental. Something quiet, something stable, something like the operating principles of existence. Whether these principles arise from nature or from a construct, does not matter in this peaceful moment. What matters is the calm awareness that the universe is deeply structured. As you sink deeper into relaxation, allow any thoughts of complexity to drift away. Instead, focus on the gentle sense of order flowing through the universe. Every star follows gravity. Every particle vibrates according to the same laws. Every moment moves forward with gentle regularity. This regularity is what lets us sleep, what lets us trust in the stability of the world around us, what lets us dream safely. The universe, whether natural or simulated, holds you gently in its patterns. Let this thought settle softly in your mind. The origin of reality may be a mystery, but the experience of reality is familiar and comforting. You are part of this vast structure. You move with its rhythms. You breathe with its flow. And as you rest, the universe continues to cradle you in its quiet, predictable harmony. The simulation hypothesis gained traction as technological progress revealed striking similarities between computational systems and physical laws. One of the most frequently referenced ideas is that the universe might operate through discrete units of space and time. In classical physics, space was treated as continuous. However, modern theories, such as loop quantum gravity, propose that space may be quantized at extremely small scales. This quantization suggests that distances cannot be divided infinitely, and that reality might have a minimum resolution. If space is pixelated in this way, it mirrors how digital simulations store information in discrete units. Another important consideration is the computational nature of physical equations. The laws of physics can be expressed using mathematical formulas that resemble algorithms. These algorithms guide the behavior of particles, fields, and forces. Maxwell's equations govern electromagnetism. Einstein's equations describe gravity. Schrödinger's equation outlines quantum wave functions. Each of these serves as a rule set similar to the underlying code of a simulation. Their consistency across the universe indicates a stable framework that operates like an organized system rather than a random collection of events. The simulation hypothesis also draws from the concept of information as the foundation of reality. Several researchers, including those in digital physics, argue that matter is essentially information arranged in specific structures. In this framework, particles become stable configurations of data. Interactions between particles represent exchanges of information. Energy becomes the ability to alter information states. If the universe is fundamentally informational, its behavior aligns naturally with the operations of a computational process. This perspective fits well with theories such as the holographic principle, which suggests that all information within a volume of space may be encoded on its boundary. Quantum mechanics offers additional elements that resemble computational processes. The phenomenon of wave function collapse raises questions about whether observation triggers the selection of specific outcomes. Some have compared this to the rendering process in computer graphics, where details are generated only when needed. While this analogy is not proof, it highlights a structural similarity between quantum behavior and efficient information handling. Observable properties appear only after interaction, suggesting that the universe may conserve informational resources in ways that parallel simulations. Another area of interest is cosmic uniformity. Measurements of the cosmic microwave background reveal an extraordinary level of smoothness across the observable universe. This smoothness is puzzling because regions separated by vast distances should not have been able to influence each other according to classical models. Inflation theory attempts to explain this, but the simulation idea offers another viewpoint. In a simulated environment, uniform initialization would be expected. The background conditions could be set globally before the system begins evolving. This would naturally produce a universe that starts in a highly even state. Modern computing also offers a perspective on complexity. Complex systems can emerge from simple rules applied repeatedly over time. Cellular automata such as Conway's game of life demonstrate that extremely simple instructions can generate intricate patterns resembling biological and cosmological structures. This emergent behavior is similar to natural processes including star formation, weather patterns, and population dynamics. If the universe operates according to fundamental rules that generate complexity through repetition, it would be consistent with a simulated framework where simple code leads to complex outcomes. One often discussed idea within the simulation hypothesis is the limit imposed by the speed of light. In digital systems, maximum speeds exist due to constraints in information transfer. If the universe were simulated, a maximum speed might represent the upper boundary of data transmission. The speed of light functions as such a limit. No known particle or signal can exceed it. This uniform constant across the universe resembles a system-wide rule designed to maintain coherence. The existence of this limit does not prove simulation, but aligns with the behavior of controlled computational environments. The hypothesis also raises questions regarding resource allocation. In simulations, unnecessary details are minimized to conserve computational power. Some scientists have proposed that distant or unobserved regions of space may not contain full complexity until interaction occurs. This concept connects to quantum indeterminacy and the idea that certain properties exist only as probabilities until measured. The universe may therefore display properties of computational efficiency, optimizing information processing and reducing unnecessary detail. Although the simulation hypothesis remains speculative, it provides a unifying framework that connects quantum physics, digital theory, cosmology, and information science. The observable universe behaves in ways that are compatible with structured computation. Whether this structure arises naturally or artificially remains unknown, yet the parallels encourage continued study. Many researchers acknowledge that the universe resembles a stable, predictive algorithmic system. Its laws remain consistent over billions of years. Its patterns repeat across scales. Its behavior often aligns with efficient information processing. The question of whether reality is a simulation cannot currently be answered definitively. However, the value of the hypothesis lies in the way it reframes scientific inquiry. It encourages consideration of the universe as an information-based structure. It highlights patterns that might otherwise be overlooked. It invites comparisons between computation and physical law, and it underscores the remarkable regularity of the cosmos. Regardless of the final explanation, the universe continues to operate with the same stability, precision, and order that have guided it from its earliest moments. The simulation hypothesis becomes more complex when examined through the lens of computational limits. If the universe operates like a type of information processing system, it would likely exhibit boundaries where certain values cannot exceed fixed quantities. These boundaries appear in several areas of physics. The Planck length represents the smallest meaningful unit of distance. The Planck time represents the smallest interval in which events can occur. These values act as natural limits embedded deep within physical law. If reality were continuous, no such discrete boundaries would be expected. Their existence suggests that the universe may operate through quantized steps, similar to the way digital systems function using discrete units. Another important aspect involves entropy and information flow. In thermodynamics, entropy measures disorder. In information theory, it is linked to uncertainty and the amount of information required to describe a system. When analyzing black holes, physicists discovered that the entropy of a black hole is proportional not to its volume, but to the area of its event horizon. This surprising relationship led to the holographic principle, which states that all information within a region of space may be encoded on its boundary surface. This idea mirrors how simulations often compress data onto two-dimensional structures that generate three-dimensional representations. Such parallels strengthen the notion that the universe may be fundamentally informational in nature. The behavior of particles in quantum mechanics also supports the possibility of a discretized universe. Particles possess quantized energy levels rather than continuous ranges. Electrons orbit atoms at specific energy states. Photons exhibit fixed packets of energy. Even atomic transitions occur in sudden jumps rather than smooth changes. These quantized behaviors align with the operations of computational systems, where values change in discrete units. The stability of these quantized states across the universe suggests a structured underlying mechanism that enforces uniform behavior regardless of environment. Some scientists examine the fine-tuning of physical constants when discussing the simulation hypothesis. Constants such as the strength of gravity, the mass of the electron, and the charge of the proton must fall within extremely narrow ranges for complex structures to exist. If gravity were slightly stronger or weaker, stars would not form properly. If electromagnetic forces varied, life-sustaining chemistry would become impossible. The narrowness of these ranges raises questions about why the universe appears so precisely calibrated. In a simulated environment, such fine-tuning might result from deliberate parameter selection. However, in a natural universe, fine-tuning remains one of the greatest unresolved questions in cosmology. The observable universe also displays patterns of symmetry that resemble the outcomes of engineered systems. Symmetry occurs in particles, fields, and forces. Gauge symmetries help define the interactions between fundamental elements of matter. These symmetries are so consistent that they form the foundation of the standard model of particle physics. If reality were a simulation, such symmetry would reflect the elegant structure of the underlying code. In many computer environments, symmetry leads to efficient calculations and reduced complexity. Likewise, symmetry in the universe ensures predictable interactions and stable structures. One of the more speculative areas relates to potential signatures or anomalies that might indicate the presence of a simulation. Some researchers propose that certain cosmic rays could display energy limits, consistent with the grid resolution of a hypothetical computational system. Others look for irregularities in the cosmic microwave background that might suggest rendering artifacts. These searches have not produced definitive results, but they reflect ongoing effort to understand whether physical observations reveal features incompatible with a naturally occurring universe. The absence of clear anomalies does not disprove the hypothesis. A simulation advanced enough to create a universe would likely conceal its underlying structure extremely well. The relationship between consciousness and a potential simulated universe introduces further complexity. Some theories propose that consciousness could be part of the simulation's design. Others suggest that consciousness emerges naturally from informational processes. In either case, consciousness interacts with quantum systems in ways that remain poorly understood. Observation affects outcomes. Measurement shapes behavior. Whether this occurs because reality renders details upon interaction, or because consciousness participates in the structure of physical law, remains an open question. This uncertainty feeds speculation about whether observers are essential components of the universe's information flow. Advances in artificial intelligence and virtual environments also influence discussion about the simulation hypothesis. Modern simulations already generate detailed environments with complex physics. These environments become more realistic each decade. If technological progress continues indefinitely, future civilizations may possess the ability to create simulated universes far more detailed than anything currently imaginable. In such a scenario, simulated realities could vastly outnumber original ones. This reasoning supports the idea that if simulations are possible, they are likely abundant, and statistically humans might inhabit one of them. Another component involves the computational resources required to simulate a universe. Some critics argue that simulating every particle in the cosmos would demand immense processing power. Supporters counter that a simulation might not require complete detail everywhere at once. Instead, it could generate information only when interaction occurs. This selective rendering is similar to how modern graphics engines operate. Only visible elements are rendered fully, while distant or irrelevant details remain simplified. If the universe functions similarly, it could reduce computational demands significantly. The debate surrounding the simulation hypothesis remains highly active. Some researchers treat it as a philosophical question. Others approach it as a scientific hypothesis that may eventually be testable. Still others argue that it is unfalsifiable and therefore outside the scope of empirical science. Despite these differing views, the hypothesis encourages examination of reality from a new perspective. It merges physics, computer science, information theory, and cosmology into a unified framework. In doing so, it provides a lens through which the structure of the universe can be studied with fresh insight. Regardless of whether reality is simulated or natural, its behavior remains consistent. The laws that govern particles, forces, and fields continue to operate with precision. The patterns observed throughout the cosmos suggest deep underlying order. This order, whether emergent or engineered, forms the foundation of physical existence. Understanding its nature remains one of the greatest scientific challenges. The simulation hypothesis is one path toward exploring that challenge. It does not diminish the universe. It simply reframes it as a structured system ready to be examined with careful thought and calm curiosity. The simulation hypothesis becomes increasingly compelling when viewed through the structure of cosmic evolution. The early universe displayed an extraordinary uniformity in temperature and density, despite regions being too far apart to exchange information through known physical processes. This remarkable uniformity led to the development of inflation theory, which proposes a rapid expansion shortly after the universe began. However, from a simulation perspective, such uniformity could arise from a simple initialization condition. When launching a simulation, developers often begin with a stable starting state that allows complexity to emerge gradually. The cosmos exhibits a similar beginning, a smooth foundation from which galaxies, clusters, and large-scale structures formed over billions of years. Large-scale structure itself supports the idea of underlying rule-driven behavior. The distribution of galaxies resembles a cosmic web with filaments, voids, and nodes forming patterns governed by gravity, dark matter, initial density fluctuations. Simulations of the universe created by astrophysicists produce nearly identical structures when the same physical rules are applied. This matching of natural observation and simulated outcomes suggests that the universe behaves like a system generated by a small set of governing algorithms. When basic rules are applied consistently across space, the result is a pattern that mirrors the cosmic web observed by astronomers. At the quantum scale, the simulation hypothesis intersects with the concept of computational minimalism. Quantum systems often appear undecided until measured. Properties such as position and momentum are described by probability distributions. When measurement occurs, the system resolves into a definite state. This behavior resembles the principle of lazy evaluation in computing, where a value is not fully calculated until it is needed. Although this comparison is not proof, it highlights a structural parallel between quantum mechanics and efficient computation. The universe may therefore be using a mechanism that avoids unnecessary detail until interaction requires it. An additional relevant concept is the observable limit of the universe. Beyond a certain distance, information cannot reach Earth because the expansion of space prevents light from traveling across the growing separation. This creates a natural boundary to observation. If the universe were simulated, such a boundary could function as a limit beyond which data need not be generated. Simulations often include only the environment accessible to the observer, while leaving distant regions undefined or simplified. The cosmological horizon functions similarly by restricting what is observable and possibly what is fully rendered. The structure of physical constants provides another important area of analysis. These constants remain unchanged across the observable universe. Their stability is essential for the formation of complex structures. In a simulated environment, constants would likely be fixed, parameters defined at the start of the program. Their uniformity across billions of light years is consistent with such initialization. In a natural universe, this uniformity is expected, but remains striking because even tiny variations could drastically alter the behavior of matter and energy. The precise and stable values of these constants form a foundation that resembles predefined computational conditions. The simulation hypothesis also aligns with the concept of algorithmic compression. In computational systems, complex outcomes often arise from highly compressed sets of rules. In physics, many complex phenomena can be described using elegant mathematical equations. Maxwell's equations compress the behavior of electromagnetic fields into a few lines. The equations of motion compress dynamics into simple relationships between force, mass, and acceleration. Even the behavior of large-scale cosmic structures can be reproduced using a limited set of initial conditions and deterministic rules. This compression suggests that the universe may operate using a compact underlying code, rather than a chaotic or unstructured foundation. Some theorists explore whether physical limits could represent computational ceilings. The Planck energy represents the upper boundary at which known physical theories remain valid. Above this scale, predictions break down. In computational terms, such breakdowns can occur at boundaries where resolution or processing power is insufficient. The universe also possesses a maximum information density determined by black hole thermodynamics. These limits align with the idea that physical systems may be bound by rules analogous to the maximum processing or storage capacity of a simulated environment. The concept of decoherence adds further detail to the discussion. Quantum decoherence describes the process by which quantum states lose their superposition when interacting with their environments. This transition from probabilistic behavior to classical behavior could represent a bridge between the underlying informational layer and the macroscopic world. In computational frameworks, such transitions occur when data moves from one level of processing to another, or when information collapses into a more concrete state. This parallel reinforces the view that the universe may have layered structures that function like levels of abstraction in computational systems. Some researchers investigate whether the universe exhibits digital signatures such as anisotropies or anomalies that could stem from an underlying grid. For instance, certain studies attempt to detect preferred directions in space or patterns inconsistent with continuous geometry. While results remain inconclusive, the search reflects the idea that the universe might have a lattice-like structure at its most fundamental level. If such a structure exists, it would provide strong evidence for a discretized reality consistent with simulation models. Despite the appeal of these parallels, the simulation hypothesis faces challenges. One major challenge involves the scale of computation required to simulate an entire universe with high fidelity. Although selective rendering and probabilistic behavior reduce the computational burden, the required resources may still be immense. Another challenge involves the lack of direct evidence. While physics displays features compatible with simulation, these features can also arise naturally. The hypothesis, therefore, remains speculative. Yet it continues to attract interest because it connects diverse scientific fields through a coherent framework that treats reality as an information-based structure. The scientific community remains divided on whether the hypothesis is testable. Some argue that future experiments involving quantum randomness, gravitational anomalies, or cosmic background patterns may reveal signatures of a computational framework. Others argue that if the simulation is sufficiently advanced, no experiment could expose its structure. Even so, the hypothesis stimulates research into the fundamental nature of information, physical law, and computation. It encourages scientists to ask whether the universe operates like a natural machine, and whether the boundary between natural and artificial systems may be thinner than expected. The simulation hypothesis also invites examination through the lens of information storage and retrieval in the universe. Every physical system contains a finite amount of information determined by its configuration and possible states. Black hole thermodynamics suggests that information density is limited by surface area rather than volume. This connection between geometry and information echoes the behavior of computational systems, where storage often depends on structural boundaries rather than physical space. The idea that cosmic information might be encoded at the limits of physical regions provides a framework in which the universe behaves like a vast data processing architecture. Another significant aspect involves the relationship between locality and non-locality in quantum mechanics. Classical physics assumes that interactions occur at specific points in space and time. Quantum mechanics, however, reveals phenomena such as entanglement, where two particles remain correlated regardless of distance. This instantaneous connection challenges classical notions of locality and suggests that underlying information may not be tied to spatial separation. In computational models, data structures can maintain correlations across large spaces without delay. Entanglement mirrors this behavior and implies that the universe may be connected through a deeper informational network that transcends spatial distance. The nature of randomness in physical systems also aligns with computational approaches. Many processes in the universe appear to rely on random outcomes, particularly in quantum measurements. However, true randomness is difficult to achieve even in computational systems, where algorithms produce sequences that appear random but remain governed by deterministic rules. Some theorists propose that quantum randomness may function similarly. It may not represent pure unpredictability, but rather reflect complex underlying processes inaccessible to observation. This perspective fits with a structured, simulated environment where randomness is a controlled parameter rather than an intrinsic property of nature. Cosmology provides additional clues through the distribution of energy and matter. Dark matter and dark energy remain two of the greatest mysteries in modern physics because they cannot be observed directly, yet their effects shape the universe. In a simulation framework, such unseen components could represent balancing parameters or computational shortcuts that maintain cosmic stability. Dark matter influences gravitational behavior. Dark energy drives expansion. Both could be interpreted as parameters introduced to ensure that large-scale structure evolves in a controlled way. Although speculative, this viewpoint illustrates how unexplained phenomena might align with simulation logic. The behavior of physical law across massive scales also supports a unified rule-based interpretation. Whether examining atomic transitions or galactic rotation, the same constants and equations apply. This uniformity arises naturally in mathematics, but also in computational systems, where a single rule set governs the entire simulated world. Even subtle behaviors such as the ratio between forces or the relationship between mass and energy display mathematical coherence. This coherence reflects the signature of a system built on consistent foundational rules. Such consistency allows predictions to be made with remarkable accuracy across a vast range of physical environments. A key philosophical question arises from the predictability of these laws. If the universe is governed by unchanging rules, it behaves like a deterministic program. Yet quantum mechanics introduces uncertainty. This blend of determinism and probability creates a hybrid system similar to probabilistic algorithms used in computing. Such algorithms combine structured rules with elements of randomness to produce efficient outcomes. The universe may operate through a similar balance where deterministic laws guide macroscopic behavior, while probabilistic rules govern microscopic events. This combination enhances stability and complexity, and aligns with the dynamics of sophisticated simulations. Technological development further informs the discussion. As virtual worlds grow in complexity, they exhibit increasingly realistic physical behaviors. Modern engines simulate gravity particle systems, fluid dynamics, and light propagation with high fidelity. As technology improves, these simulations approach natural realism. If such progress continues, it becomes difficult to distinguish advanced simulations from reality. This trajectory implies that sufficiently advanced civilizations could generate simulated universes with physical laws indistinguishable from their own. In that scenario, simulated observers would experience a coherent and stable environment without awareness of its artificial nature. Another element to consider is the anthropic principle, which states that the universe appears structured in ways that permit the existence of observers. Physical constants allow for stars to form. Chemical reactions permit life. Biological systems evolve complexity. From the simulation perspective, these conditions could reflect intentional design. In simulated environments, parameters are often adjusted to create desirable outcomes. Similarly, the universe may display configurations selected for stability and complexity. The anthropic principle does not prove simulation, but the alignment between life-permitting conditions and fine-tuned constants supports the possibility of intentional calibration. The nature of time also raises questions relevant to the hypothesis. In computational systems, time is represented by discrete updates. Each step of the program advances the state of the system. In physics, time appears continuous, but evidence from quantum gravity research suggests that time may be quantized at extremely small intervals. If true, this would imply that the flow of time consists of discrete updates consistent with a simulation processing cycle. The uniform directionality of time also aligns with computational logic. Programs move forward through sequential steps. The universe similarly advances only in one direction. Many researchers examine whether physical reality contains computational shortcuts. For example, certain equations become simpler when expressed in lower-dimensional representations. The holographic principle suggests that three-dimensional space might emerge from two-dimensional information. This reduction mirrors how simulations often store data in simplified formats that generate more complex visual or physical scenes. Such compression allows systems to operate efficiently while maintaining high fidelity for observers. If the universe uses similar mechanisms, it may indicate that physical reality is structured to prioritize efficiency consistent with simulation principles. The simulation hypothesis ultimately serves as a lens for analyzing the universe through the framework of information theory and computation. Its strength lies not in definitive evidence, but in the coherence it brings to diverse observations. Quantum mechanics, relativity, thermodynamics, and cosmology all hint at patterns that could arise from underlying computational processes. Whether the universe is naturally informational or artificially simulated remains unknown. What is clear is that its structure is remarkably stable, consistent, and mathematically elegant. These characteristics encourage continued study of reality as an information-based system. The simulation hypothesis also draws attention to the concept of computational universality, which refers to the ability of simple systems to perform any calculation given sufficient time and resources. This principle is demonstrated in cellular automata, such as the Rule 110 system, which is capable of universal computation despite its extremely simple rule set. The fact that such minimalistic structures can generate limitless complexity suggests that the universe could operate according to similarly compact rules. If physical laws function like algorithmic instructions, they may produce the complexity observed in galaxies, stars, planets, and biological life without requiring an excessively detailed foundational design. Furthermore, the quantization of physical properties adds significant support to the idea of a discrete underlying structure. The energy levels of electrons in atoms follow strict, quantized patterns. The vibrational modes of molecules occur in discrete steps. Even electromagnetic radiation is emitted in quantized units. These discontinuities are consistent across all observed systems. In computational environments, discrete values represent finite precision and stable states. The presence of quantized behavior in nature hints at a framework where information is encoded in stable increments rather than continuous ranges. This framework aligns naturally with the architecture of a simulation. Analysis of computational resource limits also provides meaningful context. For a hypothetical simulation of the universe to function effectively, it must manage immense amounts of data. The total number of particles in the observable universe is extremely large. However, not all of these particles require active processing at all times. Many regions of space remain empty or uniform. In a simulation environment, these areas could be represented by simplified states rather than detailed particle-level calculations. This approach resembles techniques used in large-scale simulations where inactive or irrelevant regions are approximated to preserve computational efficiency. The behavior of light provides another intriguing clue. Light travels at a constant speed in all directions, regardless of the motion of the observer. This invariance is foundational to relativity. In a computational model, a constant speed of information transfer is necessary to maintain coherence across the system. If information could move faster in some directions, the simulated world might become inconsistent. The fixed speed of light, therefore, resembles a universal data transfer rate, ensuring uniform communication across space. This interpretation reinforces the possibility that physical constants serve functional purposes similar to parameters in computational systems. Another significant topic involves the relationship between complexity and simplicity in physical equations. Many of the most fundamental laws appear elegant and compact, even though they describe phenomena of extraordinary complexity. Einstein's field equations, which govern the behavior of gravity, compress the structure of spacetime into a concise mathematical form. Maxwell's equations reduce the entire field of electromagnetism into 4 compact relationships. Such elegance resembles the structure of efficient code used in simulations. The universe appears to operate according to principles that prioritize simplicity at the foundational level, while allowing intricate outcomes to emerge over time. Large-scale cosmic simulations created by astrophysicists also highlight the feasibility of rule-based universes. When researchers input basic laws of physics into computational models, they produce structures remarkably similar to what telescopes observe in the real cosmos. Galaxy clusters form along filamentary structures. Voids emerge where matter becomes sparse. The distribution of mass and energy follows nearly identical patterns to those seen in astronomical surveys. This match between simulated and observed structure suggests that the real universe may operate under a set of rules that can be replicated computationally. The consistency reinforces the idea that our universe behaves like a simulated environment, even if its origin is natural. The simulation hypothesis also explores the possibility that quantum fluctuations and vacuum energy might represent background processes within a computational system. Quantum vacuum energy produces constant fluctuations in empty space. Particles and antiparticles appear and disappear in extremely short intervals. This background activity could be interpreted as the system's intrinsic processing noise, or the baseline energy of the underlying informational substrate. Although this interpretation remains speculative, it aligns with the idea that the universe contains a persistent computational foundation that supports observable physical behavior. The emergence of biological systems provides additional context. Life follows patterns that resemble algorithmic processes. Genetic code stores information in discrete units. Cellular systems operate through biochemical pathways that resemble computational instructions. Evolution functions as an optimization algorithm that adjusts biological traits over generations. This algorithmic nature of life aligns with the broader idea that the universe itself may operate according to informational rules. If biological systems are deeply computational, it becomes plausible that they arise within a larger computational environment. Philosophical perspectives further strengthen the hypothesis. Some interpretations of idealism propose that reality is constructed by or dependent on information or consciousness. Other schools of thought emphasize the role of perception in defining what is considered real. If the universe requires observers to collapse quantum states into definite outcomes, reality may depend on interaction rather than existing independently. This dependency shares conceptual ground with simulations where environment states become concrete only when processed or rendered. Such parallels do not serve as direct evidence, but highlight the compatibility between philosophical and computational views of existence. Another important consideration involves error correction mechanisms. Quantum error correction codes demonstrate that information in quantum systems can be preserved despite noise and disturbances. Some theorists propose that physical law itself might embed natural error correction, ensuring the stability of particles and forces. In computational systems, error correction is essential for maintaining coherence. If the universe possesses similar stabilizing mechanisms, it may indicate that physical reality contains built-in safeguards analogous to those found in simulations. Finally, the persistent regularity of physical law suggests long-term stability characteristic of structured systems. Over billions of years, gravity, electromagnetic interactions, nuclear forces, and thermodynamic rules have remained unchanged. This stability allows matter to form stars and planets. It enables chemistry to function reliably. It provides the foundation for life and conscious experience. In a simulated environment, stable rules would be necessary to maintain consistency. The unchanging nature of physical law therefore aligns with the behavior expected of a system governed by fixed computational rules. The simulation hypothesis gains additional depth when examined through the study of computational irreducibility. This concept, introduced in the context of cellular automata, suggests that certain systems cannot be simplified. Their outcomes cannot be predicted without performing each step individually. In a universe governed by computational rules, this irreducibility could explain why many natural phenomena remain difficult to predict despite simple underlying laws. Weather patterns, turbulence, chaotic dynamics, and biological evolution all exhibit behaviors that require step-by-step calculation. This requirement resembles the characteristics of algorithms that cannot be shortcut or compressed further. The existence of irreducibility in natural systems may therefore indicate that the universe operates through iterative computational processes rather than continuous analytical functions. The distribution of information in the cosmos offers another angle of analysis. Information does not appear randomly scattered, but follows predictable pathways governed by energy and entropy. In black holes, information is tied to the horizon area. In thermodynamics, information disperses through heat and interactions. In quantum systems, information remains conserved even when states become entangled or decoherent. This conservation suggests that the universe operates with strict informational accounting, similar to how simulations track state changes. Without such accounting, a system could become inconsistent. The fact that information never disappears even in extreme conditions resembles the rules of well-structured computational environments. Another important connection involves the principle of least action, which states that physical systems follow paths that minimize a particular mathematical quantity. This principle governs the motion of particles and the evolution of fields. It creates trajectories that reflect optimal solutions. In computational terms, such optimization resembles algorithms that seek the most efficient path toward a goal. Simulations often incorporate similar principles to reduce computational cost and maintain stability. The fact that nature consistently chooses paths of minimal action may indicate an underlying optimized system designed to produce orderly results through efficient calculations. The large-scale uniformity of cosmic expansion also fits within a computational interpretation. The universe expands according to the cosmological constant or dark energy, which acts uniformly across space. This uniform behavior resembles a global parameter applied equally throughout a simulation. In computational architectures, global variables influence system-wide behavior without requiring localized calculation for each region. The consistent expansion rate across the universe could therefore reflect a rule applied uniformly at the highest level of the system's structure. Another key observation involves particle indistinguishability. In quantum mechanics, all electrons are perfectly identical. They possess the same mass-charge spin and all other attributes. Their identity does not vary across space or time. In a natural universe, one might expect small variations arising from environmental differences. However, in a rule-based system, identical particles could be instantiated as copies of the same template. In simulations, reusable objects share identical parameters and behaviors. The perfect sameness of quantum particles therefore resembles the structure of templated objects within a computational environment. The existence of symmetries in physical laws adds further weight to the argument. Symmetries define how systems remain unchanged under various transformations, such as rotation, translation, or reflection. These symmetries produce conservation laws. For example, rotational symmetry leads to conservation of angular momentum. Translational symmetry leads to conservation of momentum. Such consistent relationships hint at foundational rules. In computational systems, symmetrical algorithms function more efficiently and require fewer instructions. The universe's reliance on symmetry may indicate an underlying coded structure, optimized for stability and coherence. Quantum field theory adds another layer of complexity. In this framework, particles emerge from excitations of underlying fields. These fields permeate all of space and interact according to precise equations. The existence of these fields mirrors how simulations often rely on background data structures that store initial conditions and rules. Particles act as transient states within these structures. Their properties arise not from intrinsic identity, but from localized interactions with the field. This relationship between fields and particles resembles object behavior in computational models, where entities inherit properties from the systems within which they operate. Space-time geometry itself may hold clues. General relativity describes gravity as the curvature of space-time caused by mass and energy. This curvature is calculated through elegant equations. In computational terms, geometry can be generated through algorithms that modify grid points according to rule sets. The bending of space in the presence of mass could represent the result of operations performed on an underlying informational grid. Although speculative, this interpretation aligns with the idea that space-time may emerge from deeper computational layers rather than existing as a fundamental continuous fabric. The simulation hypothesis also interacts with quantum computing research. Quantum computers rely on qubits, which can represent multiple states simultaneously. Their ability to perform parallel computations mirrors potential behavior of an advanced simulated universe. If the underlying layer of reality functions similarly to a quantum processor, it could theoretically compute massive amounts of information simultaneously, allowing for a highly detailed environment. The connection between quantum superposition and parallel computation strengthens the view that quantum behavior may reveal characteristics of the universe's computational foundation. Another area of interest involves the concept of renormalization in physics. Renormalization adjusts equations to handle infinities and produce meaningful results. This technique resembles strategies used in simulations to maintain numerical stability. In computational systems, values that exceed certain ranges are rescaled or adjusted to keep the simulation stable. In physics, renormalization serves a similar purpose, preserving predictive accuracy by controlling divergent quantities. Such methodological overlap suggests that physical law may incorporate mechanisms comparable to those used in engineered computational systems. Cosmic background radiation provides a critical observational test for the hypothesis. If the universe is simulated on a grid, certain directional artifacts should appear in the distribution of cosmic microwave background fluctuations. Some studies have attempted to identify such grid patterns. Results remain inconclusive, but even the effort itself reflects the alignment between cosmological observation and the search for computational signatures. If future data reveals anisotropies that match expected grid patterns, It would provide strong evidence for a discretized underlying structure consistent with simulation models. The simulation hypothesis does not imply that reality is artificial in a trivial sense. Instead, it reframes physical law as a structured system capable of being described through information and computation. This perspective encourages interdisciplinary study, connecting physics, computer science, mathematics, and philosophy. By viewing the universe as an informational construct, scientists can explore fundamental questions with new tools and frameworks. Whether or not the hypothesis proves correct, its conceptual power lies in the connections it draws between seemingly unrelated fields and its ability to highlight underlying patterns that govern the cosmos. The simulation hypothesis can also be examined through the study of emergent complexity in natural systems. Many complex phenomena arise from the interaction of simple rules repeated across large scales. Snowflakes form through basic molecular interactions yet exhibit immense structural variety. Galaxies form through the gravitational collapse of matter governed by simple equations yet produce visually intricate spiral arms, filaments, and clusters. Biological evolution operates through basic principles of variation and selection, yet produces extraordinary levels of complexity in organisms. This pattern mirrors the behavior of simulated systems, where simple rule sets applied iteratively generate highly complex outcomes. The resemblance between natural emergence and computational emergence strengthens the idea that the universe may rely on underlying algorithmic processes. The existence of thresholds and phase transitions in physics also aligns with computational principles. Systems can behave very differently when parameters cross certain limits. Water transitions from liquid to solid at a precise temperature. Quantum systems shift behavior depending on energy levels. Cosmic structure undergoes transitions as density changes. In simulations, phase transitions often occur when values cross predefined boundaries. This behavior arises from discrete instructions that dictate system state changes. The presence of clear threshold-driven behavior in nature suggests that the universe may operate through logical transitions similar to state changes in computational models. Mathematical constants provide another angle of analysis. Constants such as pi Euler's number and the fine structure constant appear across a wide variety of physical equations. Their values remain fixed, no matter where or when they are measured. In a simulated environment, constants would be predefined as part of the foundational code. Their invariance across space and time reflects the behavior of programmed parameters. The fact that these constants possess specific numerical values that allow stability in the physical world adds weight to the hypothesis that they are part of an optimized rule set designed to support consistent physical behavior. The concept of computational locality is also relevant. In simulations, local interactions determine global outcomes. At each step, a program updates the state of each element based on the state of nearby elements. This locality-driven computation mirrors how the universe functions. Particles interact through local forces such as electromagnetism and the strong and weak nuclear interactions. Even gravity, despite its long-range effects, operates through curvature of spacetime, determined by local energy density. The correspondence between local rule-driven behavior in simulations and local interactions in physics suggests that similar principles may govern both natural and simulated systems. The role of symmetry breaking in cosmology provides another compelling connection. In the early universe, symmetries may have existed between fundamental forces. As the universe cooled, these symmetries broke, resulting in the distinct forces observed today. In computational systems, symmetry breaking can occur when initial conditions change or when rules evolve over time. Such events create diversity in system behavior and contribute to complex outcomes. The universe's symmetry-breaking events may reflect structured transitions within an underlying computational framework that allowed new behaviors and structures to emerge as conditions changed. Another important aspect involves the scalability of physical law. The The same rules apply at the atomic level, at the human scale, and across cosmic distances. This scalability resembles how simulations apply identical instructions uniformly across a grid, regardless of size. A simulated environment does not require different rules for different scales, unless explicitly programmed to do so. The universe's consistent laws across all scales indicate that it may operate under a unified rule set designed to maintain coherence, whether acting on particles or galaxies. This uniformity contributes to the view that physical reality may be algorithmic in origin. The behavior of vacuum fluctuations provides additional insight. Even imperfect vacuum energy appears and disappears spontaneously in the form of particle pairs. This behavior could represent background computational activity or a baseline state of the underlying information layer. In simulations, background processes often operate continuously to maintain system stability. These tasks may include updating states, performing checks, or resetting values. Quantum fluctuations resemble this background activity, suggesting that the universe may possess intrinsic informational processes that occur independently of observable events. Another field relevant to the simulation discussion is the study of error tolerance in natural systems. Many physical and biological processes include mechanisms that correct or mitigate errors. DNA replication includes proofreading functions. Quantum systems maintain coherence through entanglement and interference patterns. Physical systems often self-stabilize due to feedback mechanisms. These stabilizing processes resemble error correction routines in computational systems. If the universe is simulated, error tolerance would be essential for long-term stability. The presence of natural error correction mechanisms may therefore indicate that physical law includes built-in stability routines. The holographic principle yields further support by suggesting that three-dimensional space may emerge from two-dimensional information. In certain theoretical models, the behavior of particles in a volume can be fully described by data stored on its boundary. This concept is remarkably similar to how simulations store information in lower dimensional structures while generating higher dimensional scenes for observers. The possibility that space itself arises from encoded information aligns with the idea that the universe is fundamentally computational rather than continuous and independent. Large-scale cosmic observations provide another layer of analysis. The distribution of galaxies exhibits fractal-like patterns across certain scales. These patterns reflect repeated structural motifs that appear similar at different levels of magnification. In computational simulations, fractal geometry often emerges when iterative rules produce self-similar structures. The similarity between cosmic structure and fractal patterns reinforces the idea that the universe may rely on repetitive algorithmic operations. The fractal nature of cosmic formation suggests that a small number of rules may generate structure across multiple scales. One of the most compelling arguments arises from the potential detectability of computational limitations. If the universe is simulated, the underlying hardware may possess finite resources. This limitation could manifest in maximum energy densities, maximum speeds, or discrete spacetime units. Observations already indicate such limits through the Planck scale and the speed of light. If these boundaries reflect computational constraints, they may provide direct evidence of a simulation. While these limits might naturally arise from physical law, their existence aligns equally well with the expectations of a computational environment. Despite these parallels, the simulation hypothesis remains controversial. Critics argue that even if the universe behaves like a simulation, it does not mean it is one. Similarity does not equal identity. Natural systems can resemble computational processes without being artificial. However, the hypothesis remains valuable because it unifies diverse aspects of physics under a single conceptual framework. It encourages examination of the universe as an information-driven structure. It highlights the deep mathematical consistency of physical law, and it raises profound questions about the nature of existence and the boundaries of knowledge. Whether reality is a simulation or naturally emergent, the observable universe operates with extraordinary coherence. Its laws remain consistent. Its structures form according to predictable principles. Its complexity arises from simple foundations. These characteristics reveal a universe deeply rooted in order and information. Understanding this structure remains one of the most important scientific pursuits. The simulation hypothesis provides one path toward exploring that structure and examining the possibility that reality itself may be part of a broader informational system. The simulation hypothesis gains further support when examined through the framework of computability and algorithmic information theory. In these fields, the complexity of an object or system is measured by the length of the shortest possible description that can generate it. If the universe can be described through a compact set of physical laws, it suggests a relatively low algorithmic complexity. Such compactness is characteristic of simulated environments where a small number of well-defined rules produce a vast range of behaviors. The elegant structure of physical law, the uniformity of constants, and the consistency of interactions all point to a universe driven by a concise informational foundation rather than an arbitrarily complex natural mechanism. Another significant element is the distinction between continuous and discrete mathematics in physical theories. Historically, physics assumed a continuous universe where space-time, energy, and matter changed smoothly. Modern theoretical developments challenge this assumption. Quantum mechanics introduces discrete energy levels. Quantum gravity research suggests discrete space-time intervals. These discrete structures resemble how computational systems operate through finite increments and limited precision. In simulations, values cannot vary continuously because computers process information in discrete steps. The presence of discretization in fundamental physics aligns with this computational architecture and raises the possibility that continuity is only an approximation of deeper digital processes. The structure of particle physics also supports this interpretation. Elementary particles behave not as tiny solid objects, but as excitations of underlying fields. These excitations appear quantized and identical across the universe. Their behavior is governed by symmetries encapsulated in group theory. Such symmetries function like transformation rules that determine how fields change. In computational systems, similar rule sets dictate how objects evolve over time. The standardized behavior of particles across the cosmos suggests they may be instances of a single underlying template applied repeatedly. This templated structure aligns with digital environments, where identical objects share the same data and rule sets. Another angle involves the limits of predictability in physical systems. Chaotic systems such as weather turbulence and orbital interactions exhibit sensitive dependence on initial conditions. Although governed by deterministic equations, their outcomes cannot be predicted accurately without precise calculations. This behavior reflects computational irreducibility, where certain processes cannot be simplified. One must compute each step to determine the next. The existence of chaotic dynamics in nature implies that the universe may operate through processes that unfold step by step, consistent with computational updates. Rather than using closed-form continuous equations, reality may evolve through iterative calculations that mirror algorithmic progression. The relationship between energy and information provides additional support. Landauer's principle states that erasing one bit of information requires a minimum amount of energy. This link between physical processes and information processing suggests that the universe treats information as a physical quantity. Black hole thermodynamics further strengthens this connection by tying entropy and information to surface area data. These findings imply that physical systems behave like information processors, subject to energetic constraints. In a simulated universe, such constraints would reflect limitations imposed by the computational substrate. They ensure efficient operation and prevent infinite growth of informational content. Another important connection involves cosmic consistency. Observations across the sky reveal that fundamental properties, such as the cosmic microwave background temperature, vary only slightly. These variations follow predictable, statistical patterns. Such uniformity resembles initialization procedures in simulations where developers set global conditions before allowing the system to evolve. Inflation theory attempts to explain this uniformity, but from the simulation perspective, it could simply reflect a starting configuration designed to promote stable cosmic development. The statistical noise observed in the cosmic background would then mirror random seeds used in simulations to generate realistic variability. The simulation hypothesis also interacts with the concept of computational energy limits. If the universe is a simulation, the system running it would possess finite computational resources. This limitation could manifest through maximum energy densities, maximum speeds, and maximum information transfer rates. The speed of light functions as a universal limit on information propagation. The Planck scale imposes lower bounds on measurable intervals. These constraints appear woven into the fabric of reality. In computational systems, similar limits exist due to hardware constraints and processing capabilities. The correspondence between physical and computational limits suggests a possible connection between the two. Another intriguing concept is the possibility that the universe may employ shortcuts to reduce computational cost. Simulations often use strategies such as level of detail rendering, where only the observed region is rendered with full precision, while distant regions remain simplified. In physics, the observable universe appears vast, but inaccessible regions beyond the cosmic horizon may not require detailed representation. Only regions that interact with observers need to possess full physical detail. This concept resonates with quantum measurement, where unobserved states remain in probabilistic superposition until interaction. Both processes reduce computational burden by generating specific outcomes only when necessary. The emergence of spacetime from quantum entanglement provides an additional line of evidence. Some theoretical models suggest that the geometry of spacetime, including its curvature and structure, arises from networks of entangled quantum states. If true, this implies that spacetime is not fundamental but emergent. In computational terms, emergent geometry could arise from algorithms that generate spatial relations based on informational connections. The idea that spacetime itself is a derived property aligns with simulations where space is generated through grid structures or mathematical mappings rather than existing independently. The study of quantum complexity deepens this connection. Quantum systems evolve through operations that increase computational complexity over time. This complexity reflects how information becomes distributed across particles. Some researchers propose that the growth of quantum complexity mirrors the expansion of spacetime or the development of gravitational fields. If the universe is fundamentally computational, such complexity growth could represent the underlying processing that drives physical evolution. The correlation between physical behavior and informational complexity further supports the idea that the universe may function like a sophisticated computational network. Another aspect worth considering is the nature of physical constants as potential tunable parameters. In a simulated environment, developers can adjust constants to achieve desired outcomes. Fine-tuning may indicate that the universe's constants were selected to produce stability, complexity, and long-lived structures. Small deviations in these constants would lead to drastically different universes, many of which would not permit star formation or chemical bonding. This precision supports the view that constants may reflect selected values within an optimized program, rather than random properties of a natural universe. Although the simulation hypothesis remains speculative, its explanatory power is noteworthy. It unifies diverse aspects of physics under a single framework centered around information and computation. It explains quantization, discrete structures, symmetry, and consistency. It integrates cosmology, particle physics, quantum theory, and information science. Whether or not reality is simulated, the hypothesis brings coherence to multiple observations. It treats the universe as an orderly, structured system governed by mathematical rules and informational processes. This perspective encourages deeper study of reality's foundations and invites new approaches to understanding the nature of existence.